Welcome back. Throughout all the exercises on data visualization, we'll be making use of an online, cloud-based environment called Google Colaboratory, aka Google Colab. So to complete these lessons, you will need a Google account, which is free. And if you don't already have a Google account, you need to go to accounts.google.com and create one. Then point your browser to this address, colab.research.google.com. If you're not already logged into a Google account, you'll be asked to log in, so do that. And one way or another, you should wind up at this dialog. Notice this New Notebook option on the bottom right? Yep, go ahead and click right there. This should open up a new cloud-based document with an IPYNB extension. This is the extension for a type of document that's called a Jupyter Notebook. Jupyter Notebook is the underlying technology that Google Colab is built upon. It's an open source technology that's very widely used in data science related fields. Though it can be used with other languages, it's got a pretty special relationship with Python because it originally evolved from a purely Python project. In fact, the PY in Jupyter is short for Python. So if you know Python and you're interested in data science, this is going to be a crucial technology to get to know. Here's a quick look at the website for Project Jupyter. It calls Jupyter Notebook the original web application for creating and sharing computational documents. A web application for creating and sharing computational documents. What does that mean? Well, we know what a web application is. Basically, that's an application that runs in a web browser. For creating and sharing computational documents, what does that entail? Let's check it out. Let's go back to our untitled notebook. And first things first, let's give this notebook a name of pyplot.ipynb. This file will be automatically saved to your Google account's drive. Now this right here is called a Jupyter code cell. We can write Python code right into the cell. Let's start by adding a couple of imports. Go ahead and type this in along with me on your end. We're going to import numpy as np, then we'll import matplotlib.pyplot as plt. NumPy and matplotlib are third-party Python libraries. They are pre-installed into this environment, along with many other popular data science libraries, so we don't need to install them ourselves, which is an advantage of using Google Colab. Now, you see this play button next to the cell? We're going to click that in just a second to run our imports. But before we do, I want you to pay attention to where it says Connect over here on the upper right. You don't need to click it. As soon as you click the play button next to the code cell, your notebook will automatically connect to a cloud-based Linux runtime environment. Go ahead and click the play button now. At this point, you should see these messages at the upper right to show that you're being connected to a runtime environment. Once the connection is completed, the import code inside the cell will run, and you should see a green check mark to its left if all went well. If you see an error message instead, check first for typos. If all went well, that means these imports are now available to us and we can use them in subsequent code cells. We're going to click the Add Code button up here to add a new code cell below the last active cell. And in this new cell, we're going to declare some Python lists. And they're going to be lists that contain floats, which are numbers with a decimal point. We're going to have 4 lists, x1, y1, x2, y2. It's not important what the values of these floats are, but it is very important that each list has exactly 4 values, and I'll explain why in a minute. But let's just go ahead and make these lists for now. So x1 has 4 floats, y1 has 4 floats, 4 more floats for x2, and we can also use integers, it doesn't really matter. Then go ahead and run this cell with the play button too. And what that does is store the variables in the running memory of our notebook. It's kind of like we're running a program piece by piece. You should see a green check mark here, too. That confirms that these variables were created, and we should be able to access them from any other code cell. Let's demonstrate this. We'll make another code cell. And remember that we imported the matplotlib.pyplot module into this notebook as plt, right? And that means that we can access the functions of that module. And it has a function called plot, which we can use here to generate a graph by calling it twice, like this. First, we'll call plt.plot, and we'll pass a few arguments to it. The first two are going to be x1 and y1, and the third will be a label variable set to the string of first plot. This represents the first line that we're going to plot on our graph at the x and y points in the x1 and y1 arrays. And second, we'll call plt.plot one more time, and this time we'll give it x2 and y2 and the label of second plot. Finally, we'll call another function named plt.legend to give our graph a legend using those labels that we passed to the plot function. And you'll see what that does in a moment. Now, if you go ahead and run this cell, you should see a simple line graph of 2 lines, like this. Notice that each line is composed of a series of x values and their corresponding y values, which we provided via the arrays. And that's why the number of values in each array is important. Each plot needs a set of x and y values that have the same length, because you can't plot an x without a y and vice versa. We can try violating that rule. Let's see what happens. Go ahead and take one number out of any of these lists, so that there's only 3 in it. Then rerun this cell to recreate these lists in memory. Then rerun the cell below it, and you should see an error message like this saying that x and y must have the same first dimension, but have shapes of 4 and 3. So that's actually a pretty helpful message as error messages go. It's telling us that we passed a list for the x-axis that has a length of 4, and a list for the y-axis that has a length of 3, and it doesn't like that. We're plotting in 2 dimensions here, the x dimension and the y dimension, and that means for each x we need a y and vice versa. So let's put that number back and rerun that cell. Then plot the graph again and make sure it works again. So you see, we have now created a computational document, and this notebook allows us to do more than run code. We can add text to it and format that text. We can add images, hyperlinks, and more to this document. Let's see an example. At the top, click this Add Text button. You see it adds a text editor at the bottom here, including ways to format that text, add links and images, and more. For an example of how this works, let's just write into it the header for our next segment, the NumPy library. You notice there's a split view where what you're typing on the left is equal to the right. That's the preview panel on the right. This text editor will format your text using a popular markup language called Markdown. So in the editor on the left, we'll enter text formatted in Markdown. And on the right, we'll see a preview of what that will look like. For example, if I click this icon here to change this text into a header, you see that it inserts a hash character, which is used in Markdown to apply a header style. And you see the preview for that on the right. And once I click out of this text editor, the editor closes and you see the text just like it looked in the preview panel. And we can share this document with others, and they can run the code on their end and edit or add to it. There are many advantages to having a collaborative, interactive environment like this for analyzing and presenting data, so you can probably begin to see why the Jupyter Notebook technology has become so popular. Next, as promised, we're going to get our first look at the NumPy library. NumPy is short for Numerical Python. Let me just write that here, back in the text cell under the header. Feel free to add this in your notebook too, if you like. One of the key features of the NumPy library is that it includes a data structure called an ND array, which is short for n-dimensional array. This can also be referred to as a NumPy array. In that basic line graph that we made earlier, we used Python lists to store the data for our x and y axis values. In data science, it turns out that what's far more common is to use a NumPy array. NumPy arrays are similar to lists, but they are designed specifically for use in data science. We can use them to store and access a large amount of numbers efficiently. NumPy also gives us a bunch of useful functions for working with numbers using these arrays. One of them is called linspace, short for linear space. And what this function does is generate a NumPy array, an ND array, that contains evenly spaced points between a start value and an end value that we provide. Let's use this function now to get an example. It will make more sense then. We'll start by adding another cell to the bottom, and we'll make a variable called num, which we'll use for the desired number of points that we want to generate. Next, let's make a variable x. This variable will hold our NumPy array. Then for its value, we're going to use the return value from calling np.linspace. Remember that earlier we imported NumPy as np. So when you see np, that means that we're using the NumPy library. Then in this function call to linspace, we're going to pass 3 arguments. The first 2 are the start and stop values for our interval, and we'll use 0 and 20. So this will generate numbers between 0 and 20 inclusive. Then the third argument says how many total numbers we want to generate. And we can use our num variable here, so we're going to generate 100 numbers. Then just so that we can see what gets stored in x when this code is run, let's print x. And now we're ready to run this cell. And when you run it, you should see an array of numbers that looks exactly like this. This is showing us 100 numbers from 0 to 20 inclusive, with even intervals between each number. This array looks very similar to a Python list, but the underlying data structure here is an ND array, aka a NumPy array. You might wonder, what's the point of making an x-axis from an array like this? Well, what is an x-axis, the horizontal axis, very commonly used for in a graph? It's quite often used to represent time. So this is giving us a way to represent, say, 20 seconds or 20 minutes or 20 hours divided into 100 intervals. And let's say we have an array containing values for the y-axis that represent data points that we're tracking over those same time intervals. And let's say that we have an array containing values for the y-axis that represent data points that we're tracking over that time, like stock market data or electrical activity or something like that. For now, just to illustrate how this works and to see another way to use NumPy, we're going to generate an array of random values for the y-axis. And we can do this using NumPy's random.rand function. Let's see what that looks like. Go ahead and add another code cell, and in it, let's make a variable called y. And it's going to hold an ND array that's returned from calling np.random.rand with an argument of num. Where are we getting this num value from? Remember, we initialized the value of num up here to hold the value of 100. As long as we have run this code cell where num was set to 100, other code cells are going to have access to that variable as well. And let's print y so we can see what's in it. Then when you run this code cell, you should see an array with 100 values, and these values are randomly spaced between 0 and 1. Of course, these are randomly generated, so what you see in your notebook will look different from mine. Now we have an array of 100 x values, and we have an array of 100 y values. So we're ready to make a graph. In a new code cell, let's use plt.plot once again to plot these arrays together. And when you run this cell, you should see a graph like this, where the x intervals are regular, but the y points are random and chaotic. Kind of looks like the stock market, right? Or Bitcoin, or whatever you kids are into these days. And you see how nice that is, that we can separate out code into cells like this and run each one at a time, so we can see and test the output from each one before we continue. We could run all the code in all these cells at the same time, in the same cell, but this approach does make it easier for us to see what's going on and to figure out where any errors are happening. That pretty much wraps it up for this exercise. You've now seen how to use the Jupyter Notebook's code and text cells inside the Google Colab environment. And you've seen how we can use the matplotlib and NumPy libraries to plot basic line graphs, and how we can use NumPy's linspace and randomRand functions to generate values in NumPy arrays. In the next exercise, we're going to look at a different kind of plot called a scatter plot. Whenever you're ready, join us there.